Welcome back to the deep dive. We have been on quite a journey with our fictional metabolic detective Medlock Holmes, haven't we?
We certainly have. It's been a long road of tracking consumption, of following the energy downstream.
Exactly. I feel like for the last few sessions, we've been standing at the exhaust pipe of life. We've watched catabolism break molecules down. We've seen the citric acid cycle just strip out electrons like a chop shop.
And then we watched oxidative phosphorylation turn all of that destruction into, usable currency, into ATP.
It's all been about how life spends energy, how it cashes the checks.
That's a fair assessment. We've really been looking at the engine of the biological car, seeing how it burns fuel. But today, we are pivoting. We're doing a complete 180.
Today we are going upstream. We are going all the way to the source.
The origin story of biological energy.
Photosynthesis. And before anyone tunes out thinking, wait, I'm studying medicine, not botany. I don't need to know about leaves. Just hold on a second. Because looking at the source material today, and we should say this is specifically Lehninger, this is arguably the most important biochemical process on Earth.
It is. And for the medical student or the clinician listening, the really fascinating thing is that photosynthesis is, it's essentially oxidative phosphorylation running in reverse.
That's the aha moment for me right there.
If you mastered the mitochondria in our previous deep dives, you already know the machinery of the chloroplast.
It's the same part.
It's the same parts, just reconfigured for a different purpose.
Yeah.
So instead of burning fuel to make a gradient, we are using light to build a gradient and then make the fuel.
So our mission today is to track a photon, a single packet of light energy from the moment it hits a leaf through this, this insane pinball machine of proteins.
That's a good way to put it.
Until it forces a molecule of carbon dioxide, which, let's be honest, really doesn't want to be involved, into becoming part of a sugar molecule.
That is the mission. And we have to be clear here. Our usual companion text, Harper's Biochemistry, it actually skips this chapter entirely. It just assumes you know it from undergraduate biology.
So this is a Lehninger special.
This is a Lehninger special, yeah. We are going deep into the conceptual clarity and the structural mechanics because, and this is the key, understanding this reinforces your understanding of human metabolism.
It's like studying a mirror image to understand the original object better.
Precisely. It shows you how the same fundamental principles of bioenergetics gradients, electron flow, ATP syntheses, can be repurposed for a completely opposite goal. Anabolism instead of catabolism.
Okay, let's start with the absolute basics then, the physics. Because this isn't just chemistry. This is, it's quantum mechanics happening in a meadow. To understand photosynthesis, you have to understand the nature of the fuel.
You have to understand light, visible light specifically. We're talking about electromagnetic radiation in that, 400 to 700 nanometer range. The rainbow, essentially.
And Lehninger introduces a term here that I love just because it sounds so formal, the Einstein.
An Einstein.
Not the physicist with the hair.
Well, named after him, naturally. But in photochemistry, an Einstein is 1 mole of photons.
So 6.022 times 10 to the 23rd photons.
Right. It's Avogadro's number, but for light particles.
That is a lot of light. Why do we need a specific unit for moles of light? Why is that important?
Because photosynthesis is a stoichiometric process, and this is a really crucial concept to grasp. 1 photon moves 1 electron. It is a one-to-one quantum interaction.
It's not like water pressure, where more pressure just means more flow in a vague sense.
Exactly. It's not a fluid dynamic situation. It is quantized. Each photon delivers a discrete packet of energy, and that energy does one specific job. It excites 1 electron.
But here's the problem that stood out to me in the notes. A single photon of, say, red light has plenty of energy to lift an electron to a higher energy state to excite it, but photons are slippery, they're fast, they hit, and the energy's there for, a nanosecond?
Less, even. It dissipates incredibly quickly as heat or re-emitted light if you don't catch it.
So you need a net.
And biological systems have evolved a very, very specific kind of net. We call them chromophores. These are simply light-absorbing molecules. And the king of them all is chlorophyll.
I looked up the structure of chlorophyll compared to heme, which we've talked about endlessly with hemoglobin and cytochromes, and it's just uncanny.
It's beautiful, isn't it, the molecular convergence?
They're almost identical rings, protoporphyrin rings. But where heme holds an iron atom in the center like a jewel, chlorophyll holds magnesium.
A magnesium ion, Mg2 plus LAP.
Why the swap? Why not just use iron? Nature loves using iron for everything electron-related.
Well, think about what iron does in the body. Iron is a redox transition metal. It loves to swap between Fe2+ and Fe3+ arene. It's a fantastic carrier of electrons, like in the cytochromes, or a binder of oxygen.
Okay.
But in this initial step, in the antenna complex, we don't want the metal to steal the electron just yet. We just want to absorb the energy of the photon. Magnesium is chemically stiff, you could say. It coordinates the ring structure, it holds it rigid so it can resonate perfectly with the light, but it doesn't engage in redox chemistry itself. It allows the whole molecule to act like a perfect tuning fork for light without short-circuiting the process.
That makes a lot of sense. And there's one other major structural difference. Heme is usually buried inside a soluble protein, right? Like hemoglobin. But chlorophyll has this long, oily tail.
A vital side chain. It looks like a kite with a very long string.
And that string is super hydrophobic.
Which tells you immediately that it anchors the chlorophyll into a membrane. This whole process is a membrane-bound event. It's not happening in some kind of cellular soup. It's happening on a two-dimensional surface. And that topology is absolutely critical for generating the gradient later on.
Okay, so we've got our main pigment, chlorophyll. We see a leaf, and it looks green. That's because it's absorbing red and blue light and reflecting the green wavelengths back at our eyes.
Right. But if you only absorbed red and blue, you'd miss a huge chunk of the solar spectrum.
All the yellows, the oranges, the teals.
Which is why plants use accessory pigments. Things like carotenoids, beta-carotene, which makes carrots orange, or lutein, and also phycobilins in some organisms.
And what's their job? Just to fill in the gaps?
Two jobs, really. First, yes, to fill in the gaps. Leninger calls this expanding the action spectrum. They absorb the wavelengths that chlorophyll misses and funnel that energy into the system. It's like having a radio that can pick up AM and FM. You just catch more signal.
And the second job?
Protection. Absorbing all this light energy is dangerous. You can form reactive oxygen species. Carotenoids are fantastic at quenching those, at acting as antioxidants. They're like the system's safety valve.
So we've got hundreds of these pigment molecules, chlorophylls, carotenoids, all packed together in the membrane. A photon hits one. What happens next? I love the funnel analogy here.
Yes, because the energy moves in a very specific way. It's not like a baseball being thrown from one molecule to another. The electron itself doesn't actually jump from pigment to pigment in this initial phase.
No, that seems like a common misconception.
It is. The process is called excitant transfer, or resonance energy transfer.
Walk us through that.
Okay, think of a room full of identical tuning forks. If I strike one tuning fork in the corner, and it starts vibrating, and I bring it close to another one, the second one will start vibrating, and the first one will stop.
Right. The vibration move?
The vibration moved. The energy moved.
Yeah.
But the physical tuning fork didn't go anywhere. That's an excitant. It's a quantum of energy, of excitement, that is passed between adjacent chromophores.
So you have this field of antenna molecules, this huge array of them, and this vibration or excitant is just bouncing around, being passed from one to the next. It's like a scream passing through a crowd.
Exactly. And the whole array is structured like a funnel. The pigments on the outside absorb higher energy, light bluer light, and they pass the energy inward, downhill, to pigments that absorb slightly lower energy light.
So the energy always flows in one direction.
It always flows toward the center, towards a very specific spot. The reaction center. This is the drain in the sink. All that harvested energy from hundreds of pigments eventually funnels down to a special pair of chlorophyll molecules.
And this is where the physics changes. This is the moment of truth.
This is the photochemical event. Because in the reaction center, that vibration, that excitant, finally hits an electron so hard that the electron doesn't just vibrate, it leaves. It physically jumps off the chlorophyll and lands on a nearby acceptor molecule.
And at that moment, you have a chlorophyll molecule that is now positively charged. It lost a negative electron. And an acceptor that is now negatively charged.
You've created a battery.
You've created a separation of charge, a redox potential.
That is it. That is the fundamental conversion of solar energy into chemical energy. Everything else that follows in photosynthesis, every single step, is just about managing that initial charge separation and preventing the electron from just falling back home.
Okay, so we've caught the energy, we've made a tiny battery, now we have to look at the machinery that uses it. And the text makes a really cool evolutionary point here. Plants didn't just invent this whole complicated system out of thin air.
No, not at all.
Yeah.
They're basically running a greatest hits album of bacterial metabolism.
That's a great way to put it.
If you look at photosynthetic bacteria that exist today, you see the prototypes. You see the component parts that were eventually stitched together.
Right, so we've got the so-called type 2 reaction centers, like in purple bacteria.
Mm-hmm. They use a system called a pheophyton quinone system. It's a cyclic setup. An electron gets excited by light, goes up in energy, passes through a couple of carriers that pump a proton, and then it falls right back down to where it started.
It just recycles the same electron over and over.
Over and over. And in doing so, it generates a proton gradient, which makes ATP, but it doesn't make any reducing power. It doesn't make NADH or NADPH. And crucially, it does not split water. It gets its electrons from something easier, like hydrogen sulfide.
So it's an electric motor, but it doesn't generate any storable fuel in the form of NADPH.
Exactly. Then you have the other prototype. The type I reaction centers in green sulfur bacteria. They use iron sulfur centers, which should sound very familiar to us.
Very familiar.
They can generate reducing power. They can make things like NADH,
Right.
but they're chemically distinct and have their own limitations.
So you have one system that's robust and great for making ATT, but nothing else. That's the purple bacteria. And another system that can make reducing power, the green sulfur bacteria.
And then cyanobacteria, the ancient ancestors of all chloroplasts, did something absolutely radical. They figured out how to wire them together.
In series.
In series. And this is the famous Z scheme of photosynthesis that you see in all the textbooks.
Why is it called the Z scheme? What's with the letter?
It's purely graphical. If you plot the energy level of the electron on the vertical axis and its journey on the horizontal axis, the path it takes looks like a sideways letter Z.
Okay, I see it now in my head. The electron gets lifted up by the first photosystem, then it falls down a bit, and then it gets lifted again by the second photosystem.
Exactly.
Why two lifts? That seems redundant. Why not just one big jump, one big photon-powered elevator?
Because of the fuel source. This is the key innovation. Plants and cyanobacteria decided to use water as their electron donor. And water is, it's everywhere. It's the perfect source. But chemically, it's incredibly stable.
It holds its electrons with an iron grip. Leninger gives the redox potential as about plus 0.82 volts.
That is very, very positive. It does not want to give up electrons. And where are we trying to send that electron?
To NADP plus SER, which becomes NADPH. And that's a high-energy molecule sitting way up at negative 0.32 volts.
Exactly. The energy gap between water at plus 0.82 and NADPH at NAD.32 is enormous. It's over a full volt. A single photon of red light, the most common type, simply does not have enough energy in its quantum packet to kick an electron all the way from water to NADPH.
It's physically impossible. The ladder is too tall for one step.
So you need two elevators. You take the electron from water, use one photon to lift it halfway up the building, that's photosystem 2. Then you let it slide down a ramp, the cytochrome complex, and use that energy to do some work, like pumping protons.
And then when it gets to the bottom of that ramp,
you put it on a second elevator, photosystem Y, and use a second photon to lift it the rest of the way to the top floor, where it can be handed off to NADPH.
Brilliant. Let's ride those elevators then. We start at photosystem 2, or PSII. Leninger calls this the engine of life.
And that's not an exaggeration. Inside PSII, there is a cluster of atoms that is, frankly, one of the most incredible structures in all of biology, the oxygen evolving complex.
The OEC.
Yes. It's a unique configuration of 4 manganese ions, 1 calcium, and 5 oxygens, all held together in what looks like a distorted chair. The Mn4CaO5 cluster.
The manganese chair. Sounds like a terrible indie band, but why manganese? What's so special about it?
Because manganese is a redox virtuoso. It can comfortably exist in multiple stable oxidation states, +2, +3, +4, maybe even +5. This flexibility is the key to solving what's called the counting problem.
Explain the counting problem.
To make 1 molecule of oxygen, O2, you need to strip 4 electrons from 2 water molecules. But as we said, photons arrive one at a time. The system gets hit by 1 photon, which moves 1 electron.
So if you just ripped 1 electron off a water molecule, you'd create a hydroxyl radical, which is bad.
Extremely bad. It would destroy the protein in a heartbeat. So the system needs a way to store the IOUs. It needs to count to 4.
The manganese chair acts like a capacitor then.
Exactly. Leninger details the S states, or Koch cycle. A photon hits the reaction center, an electron is ejected. The manganese cluster gives up an electron to replace it, and now holds 1 positive charge. That's S1.
Zap, second photon.
The cluster loses another electron. Now it holds 2 positive charges, S2. It does this 4 times, accumulating 4 positive charges, 4 holes as they're called. It's holding its breath, waiting for the count of 4.
And only on that 4th step.
Only when it has 4 accumulated positive charges, which is a massive oxidizing power, does it grab 2 water molecules, rip all 4 of their electrons at once in a concerted reaction, and release O2 as a waste product.
A waste product. The oxygen we are breathing right now, the ozone layer, the entire atmosphere that allowed complex aerobic life to evolve, it's just the exhaust fumes of this manganese chair.
It really does put it in perspective. The entire aerobic world is downstream of this one remarkable enzyme.
So the electrons are ripped from water, they fill the hole in the special pair of chlorophylls, P680. Where do they go next?
From the excited P680, they jump to a molecule called pheophytin, which is just a chlorophyll without the magnesium. From there, they go to a tightly bound ketone, PQA, and then to a mobile ketone, PQB. This was called plastoquinone.
Plastoquinone, that sounds incredibly familiar.
It should. It's the chloroplast version of ubiquinone or coenzyme Q from our mitochondria. It's a small, lipid-soluble electron carrier that can swim through the membrane.
So it picks up 2 electrons from PSII and 2 protons from the stroma and becomes PQH2.
Exactly. And then it swims over to the next major station, the cytochrome B6F complex.
And looking at the diagram of cytochrome B6F in Leninger, it looks suspiciously like complex Thur in the mitochondrial electron transport chain.
It is homologous. Structurally and functionally, they are cousins. It performs the exact same trick.
The Q cycle.
The Q cycle. We went through this in our oxidative phosphorylation deep dive, and it's happening again right here.
Let's do a quick refresh. What is the Q cycle doing?
It's an energy-saving mechanism. It takes the 2 electrons from plastoquinol, PQH2. It sends one down a high-potential path to a mobile carrier called plastocyanin. The other electron is sent down a lower potential path and recycled, helping to pump more protons.
So the main point is it couples this electron movement to proton movement.
Yes. For every PQH2 it oxidizes, it pumps a net total of 4 protons from the stroma, which is the space outside the thylakoid, into the thylakoid lumen, the space inside.
Okay, correct me if I'm wrong, but this is the heart of it. This is creating the gradient, the proton motive force.
Yes. But there's a really interesting nuance here that Leninger points out, a key difference from mitochondria.
What is it?
In mitochondria, the gradient is electrochemical. It's both a voltage difference and a pH difference across the inner membrane. But the thylakoid membrane in chloroplasts is surprisingly leaky to other ions, like magnesium and chloride.
So if you pump a positive proton in,
A positive magnesium ion can just leak out to balance the charge.
so you don't build up a huge voltage, an electrical potential.
Right. You mostly just build up a massive pH difference, a chemical potential. The lumen gets incredibly acidic down to maybe pH 5, while the stroma on the outside stays alkaline up around pH 8.
That's a 1,000-fold difference in proton concentration. That is a massive battery.
A massive chemical battery, yes. And that battery is what's going to drive ATP synthesis. But before we cash that in, we have to finish our electron's journey.
Right. Our electron is now sitting on plastocyanin.
Plastocyanin is a small copper-containing protein that's the functional equivalent of cytochrome C. It's the mobile carrier that connects the 2 big complexes.
It's lost some energy driving that proton pump, so now it needs another boost.
Enter the second elevator, photosystem I, or PSI.
This is the descendant of the green sulfur bacteria system.
That's right. Plastocyanin floats over and drops the electron off at the PSI reaction center. Special pair called P700. Light hits P700. Wham!
Right.
The electron is boosted to an incredibly high energy level, even higher than it was at the start of its journey in PSII.
And from this incredible height, it can basically just fall downhill towards its final destination.
It passes through another series of carriers, phylloquinone, then a chain of iron-sulfur centers, and is finally handed off to a soluble iron-sulfur protein floating in the stroma called ferredoxin.
And ferredoxin is the final handoff.
Almost. Ferredoxin then bumps into an enzyme called ferredoxin NADP plus oxidoreductase. And that enzyme uses 2 electrons from 2 ferredoxins to reduce NADP plus to NADPH.
And there you have it. You've taken electrons from water, a very low energy source, used 2 photons to lift them way up, pumped some protons along the way to build a gradient, and stored those high energy electrons in NADPH.
That's the linear electron flow, from water to NADPH.
But the text mentions this other mode, a cyclic electron flow. You called it a balance knob earlier. Why would the plant want to do that?
But think about the outputs. Linear flow makes both ATP from the proton gradient and NADPH from the final electron transfer. The ratio is fairly fixed, but sometimes the cell needs more ATP than it needs NADPH. The Calvin cycle, as we'll see, is an absolute ATP hog.
So if you're swimming in NADPH but running low on ATP, biology needs a switch.
And it has one. In cyclic flow, The electrons get to ferredoxin, and instead of going to make NADPH, they turn around. They're handed back to the cytochrome B6F complex.
They get back on the merry-go-round.
They get back on the ramp. They flow through the cytochrome complex again,
Pumping more protons.
which contributes to the gradient, which means you make more ATP.
But no NADPH is made, and since PSII isn't involved in the loop, no water is split and no oxygen is evolved.
Exactly. It turns the system into a pure ATP generator, just like those ancient purple bacteria we talked about. It allows the plant to fine-tune the ratio of ATP to NADPH production to match exactly what the downstream metabolic demand is. It's an incredibly elegant piece of regulation.
That brings us perfectly to Section 4, photophosphorylation, the universal turbine. We've built this massive proton gradient inside the thylakoid lumen. pH 5 inside, pH 8 outside.
And just like in mitochondria, there's only one way out for those protons. There's only one approved exit.
The ATP synthesis.
The structure is almost identical. You have the faux portion embedded in the membrane, forming the proton channel, and the F1 head sticking out, which does the catalytic work. In chloroplasts, we call them CFO and CF1, but it's the same machine.
But there's a topology twist here that confused me at first, and I think it's worth clarifying. In mitochondria, we pump protons out of the matrix into the intermembrane space, and then they flow back in to make ATP.
Correct.
Here we are pumping them into the lumen, and they flow out to the stroma. It feels completely backwards.
It does seem reversed, doesn't it? But look at where the head of the turbine is, the F1 part that actually synthesizes the ATP.
In the chloroplast, it's sticking out into the stroma.
And in mitochondria, it's sticking out into the matrix. In both cases, the stroma and the matrix are the end side of the membrane, the negative alkaline side where the protons are scarce.
So biologically, the orientation is exactly the same relative to the gradient.
Exactly the same. The ATP is always made into soup in the main compartment where all the enzymes are waiting to use it. The mechanism is universal.
Rotational catalysis. The protons flow through the channel, the central gamma stalk spins like a drive shaft, and that forces conformational changes in the head that smash AT and inorganic phosphate together.
To make ATP. And that ATP is released right into the stroma.
Okay. So now floating around in the stroma, we have our two products from the light reactions. We have a pile of ATP, which is our energy currency, and we have a pile of NADPH, which is our reducing power, our high energy electrons.
We have the battery and the bricks. Now we need to actually build the house.
Welcome to the Calvin cycle, or, as you rightly pointed out earlier, the reaction formerly known as the dark reactions.
Yeah, let's unpack that misnomer because it's really misleading. Why did they call it that in the first place?
Because the chemistry itself doesn't directly require a photon to hit an enzyme, right? It's just standard biochemistry, not photochemistry.
Correct. But calling them dark reactions implies they happen at night, in the dark. That is categorically false. As we'll see in the regulation section, these enzymes are tightly switched off in the dark.
So they should be called the light-independent but light-regulated reactions.
Which is a mouthful. Carbon fixation reactions, or just the Calvin cycle, is much better. They happen during the day, right alongside the light reactions that are fueling them.
Got it. So the goal here is CO2 assimilation. We need to take inorganic carbon, a gas, and turn it into organic solid sugar. And the star of this show is an enzyme with a massive, if somewhat flawed, reputation.
Rubisco.
Ribulose 1,5-bisphosphate carboxyloxygenase.
Just Rubisco is fine.
Leninger calls it the most abundant protein on Earth.
By mass, it is. There is more Rubisco on this planet than any other single protein, and it's arguably one of the most inefficient enzymes known.
How inefficient are we talking?
Most enzymes process thousands of substrate molecules per second. Carbonic anhydrase, which also deals with CO2, does about 1 million. Rubisco processes about 3 molecules per second.
That is painfully slow.
It's a sloth, a giant 8 large subunit, 8 small subunit molecular sloth. So to compensate for being so slow, plants just make tons of it. Up to 50% of the soluble protein in leaf can be just Rubisco.
So it's the only game in town for fixing carbon, so you just have to live with its flaws?
Pretty much. Let's look at the reaction. Stage 1 of the Calvin cycle. Fixation.
What happens?
Rubisco takes a 5-carbon sugar, which is already present in the stroma, called ribulose 1,45-bisphosphate. It grabs a CO2 molecule from the air, and it smashes it onto that sugar.
So 5 carbons plus 1 carbon gives you a 6-carbon molecule.
Briefly, for a fleeting moment.
Yeah.
That 6-carbon intermediate is incredibly unstable. It instantly gets hydrated and snaps in half.
To make what?
2 identical 3-carbon molecules called 3-phosphoglycerate, or 3-PGA.
Wait a minute, 3PG, yeah, that sounds really familiar. That's a glycolysis intermediate.
It is indeed. And that's a
Yeah.
key theme here. The Calvin cycle is, in many ways, just glycolysis running in reverse. We are building up the very molecules that we usually break down for energy.
Okay, so that's stage one. We've fixed the carbon. It's now part of an organic molecule. But 3PGA is an acid, a glycerate. We need to make a sugar, an aldehyde. We need to reduce it.
Which brings us to stage 2, reduction. This is where we pay the bill. This is where we use the products of the light reaction.
We use the ATP and the NADPH.
First, an enzyme uses ATP to phosphorylate 3-PGA, activating it. Then another enzyme uses NADPH to reduce that molecule.
And we get glyceraldehyde 3-phosphate, G3P, the exact same G3P from glycolysis.
The very same. Now, here's where the math problem comes in, the accounting of the cycle.
Lay it on us.
For every 3 molecules of CO2 that we fix, we go through the cycle and we generate 6 molecules of G3P. Now, one of those 6 molecules is pure profit.
The 1 in 6?
That's the one that can leave the cycle. It can be exported from the chloroplast to become glucose or sucrose for transport or stored as starch right there in the chloroplast for later. That is the biomass.
And the other 5? What happens to the other 5 G3P molecules?
The other 5 have to stay in the casino. They are reinvested. They enter stage 3, regeneration.
This is the part of the diagram in the textbook that looks like a bowl of spaghetti. All the arrows going everywhere.
It is the complex shuffle, yes. It looks intimidating, but the logic is simple. We have 5 3-carbon molecules. That's 15 carbons total. We need to rearrange them to reform 3 5-carbon molecules of ribulose, 1-polyphosphate, also 15 carbons total.
So you start the cycle over again.
You regenerate the acceptor molecule. It involves a series of reactions using intermediates with 3, 4, 6, and 7 carbons. It's biochemical origami. But it's essential. If you don't regenerate the landing pad for CO2, the whole cycle grinds to a halt.
And this regeneration costs more energy, doesn't it?
It costs more ATP, yes, to phosphorylate the final ribulose 5-phosphate. So the overall cost to fix 1 CO2 is 3 ATP and 2 NADPH.
It's an expensive process. Now, there's a specific transporter that Leninger highlights that I found fascinating because it seems so simple but so critical. The pitriose phosphate antiporter.
This is the gatekeeper. It's the bottleneck for the entire system of photosynthesis for the whole plant.
Explain this. Why is a simple transporter so critical?
Okay, so photosynthesis is happening in the chloroplast stroma. We're making our G3P, our triose phosphate. We want to send that G3P out to the cytosol to make sucrose, which can then be sent to the roots, the fruit, everywhere else.
Right, export the fuel.
But G3P, triose phosphate, contains a phosphate group. If you just keep shipping phosphate out of the chloroplast attached to the sugar, the chloroplast will very quickly run out of free inorganic phosphate.
And without inorganic phosphate, you can't make ATP. Remember, ATP synthase needs ADP plus pi.
Exactly. If the inorganic phosphate pool in the stroma dries up, the turbine jams. Photophosphorylation stops. The light reactions stall. You get a backlog of high-energy electrons, and that can cause massive oxidative damage to the cell.
So this antiporter is a strict accountant. It's a one-for-one deal.
It's an obligatory exchange. For every 1 triose phosphate molecule that goes out to the cytosol, 1 inorganic phosphate pi must come in.
It balances the phosphate books.
Perfectly. It ensures that the chloroplast never runs out of the raw material for ATP synthesis. If this transporter is blocked, or if the plant is growing in phosphate-poor soil, photosynthesis stops dead no matter how much light you shine on it.
That connects beautifully to Section 6, regulation. We said earlier that these dark reactions actually only run in the light. How do these enzymes like Rubisco know the sun is shining? It's not like they have little eyes.
It's not magic. It's just very clever chemistry. The plant uses the direct byproducts of the light reactions as internal signals. There are 3 main ways this works.
Give me the first one.
pH. We just talked about it. When the light reactions are running, they are pumping protons from the stroma into the thylakoid lumen.
Which means the protons are leaving the stroma. So the pH of the stroma goes up. It becomes alkaline.
It goes from about pH 7 in the dark to pH 8 in the light. And it just so happens that Rubisco and other key Calvin cycle enzymes have evolved to have a pH optimum of around 8. They are literally turned off at the neutral pH of the dark stroma. They use the alkaline environment as a green light signal.
That's incredibly clever. What's the second signal?
Magnesium. Remember our leaky membrane. When protons pump into the lumen, positive ions have to move out to the stroma to balance the charge. That ion is primarily magnesium.
So when the light is on, the stroma gets flooded with magnesium ions.
And Rubisco absolutely requires magnesium for its function. The Mg2 plus ion sits in the active site and coordinates the substrates. It polarizes the CO2 molecule to make it ready for attack.
Yeah.
Without a high concentration of Mg2 plus terema, Rubisco is inactive.
So high pH plus high magnesium equals the sun is out, get to work.
It's a two-factor authentication system.
And there's a third, even more elegant mechanism, the pyridoxine system.
This is a beautiful redox-based system. It involves disulfide bonds. You know these from protein structure. They're covalent bridges between two cysteine sulfur atoms that lock a protein into a certain shape.
Like a chemical padlock on a gate.
A perfect analogy. In the dark, several key Calvin cycle enzymes are oxidized. They have these disulfide bridges, SS, that lock them in a catalytically off state.
So how do we find the key to unlock the padlock?
The key is the electron flow itself. When the sun shines, electrons are flowing from photosystem I to ferredoxin. If there's plenty of light, and ferredoxin is abundant and reduced.
A signal of high energy input.
Right. Some of those high-energy electrons from ferredoxin are diverted. They're passed to a small soluble protein called thioredoxin.
So thioredoxin picks up the electrons, it becomes reduced.
And reduced thioredoxin is the key. It floats over to those locked-up enzymes and passes its electrons to their disulfide bonds. It reduces them. The SS bridge breaks and becomes two SH groups. The padlock opens. The enzyme changes shape and turns on.
That is so incredibly clever. The electrons themselves, the direct product of the light reactions, are the physical signal to activate the dark reactions.
It ensures that the energetically expensive machinery of building sugar only runs when there's ample power to run it. You absolutely do not want to be building sugar in the dark at the same time glycolysis is trying to burn it. That's a classic futile cycle.
Speaking of futile cycles, we need to talk about the elephant in the room. Section 7. The bug in the system.
Photorespiration, the flaw in the machine.
So, Rubisco. We said the full name is ribulose 135 bisphosphate carboxylase oxygenase. The name admits the problem.
It's written right on the tin.
It's supposed to bind CO2, that's the carboxylase activity, but sometimes it gets confused, and it binds oxygen instead.
And it happens a lot. At current atmospheric conditions, it happens about once every 3 or 4 turnovers of the enzyme. That is a massive error rate for a biological system.
Why? I mean, oxygen and carbon dioxide don't look that much alike to me. Why is nature's most important enzyme so sloppy?
Well, to an enzyme active site that's dealing with small gas molecules, they can be tricky to distinguish. But the real reason is likely evolutionary history. When Rubisco first evolved billions of years ago in ancient cyanobacteria, there was almost no oxygen in the atmosphere.
So it didn't matter if it wasn't perfectly specific because the wrong substrate just wasn't there to distract it.
Exactly. But then, thanks to the wild success of photosynthesis and that manganese chair, the atmosphere filled with oxygen. Rubisco became a victim of its own success. It terraformed the planet, and in doing so, created an environment where its own intrinsic flaw became a major liability.
So what happens when it grabs an oxygen molecule instead of CO2?
It's a disaster. Instead of making 2 useful molecules of 3-PGA, it breaks the ribulose 1,4,5 bisphosphate into 1 molecule of 3-PGA, which is fine, and 1 molecule of a 2-carbon compound called 2-phosphoglycolate.
And 2-phosphoglycolate is?
Useless. Actually, worse than useless. It's a metabolic poison. It's an inhibitor of other enzymes in the Calvin cycle. The plant has to get rid of it, and has to do it quickly.
And the cleanup process is what we call photorespiration.
It's a massive salvage operation, and it is incredibly messy. As Leninger shows, it involves a convoluted pathway that snakes through 3 different organelles. It starts in the chloroplast, that goes to the peroxisome, and then to the mitochondria before coming back.
It's a huge detour, and it must cost energy.
A ton of energy. It consumes ATP, it consumes NADPH, it consumes more oxygen, and in the ultimate irony, in the mitochondrion, it releases CO2.
It releases CO2. It literally undoes the work of photosynthesis.
It is breathtakingly wasteful. In many of our most important crops, what we call C3 plants like wheat, rice, soybeans, photorespiration, can reduce the efficiency of photosynthesis by 20, 30, even 40% on a hot, sunny day.
So nature, being resourceful, found a workaround, a patch, the C4 solution.
It's the C4 plants that evolved in hot, bright, tropical environments like corn, sugarcane, sorghum. They evolved a patch for Rubisco's buggy software.
The text describes this as a spatial separation.
Right. The core idea is simple. If Rubisco is bad at distinguishing CO2 from oxygen, the solution is to put Rubisco in a special room where there is no oxygen and tons of CO2.
A VIP room for Rubisco.
A VIP room. And in C4 plants, this room is a layer of cells deep inside the leaf called the bundle sheath cells. They're tightly packed, and gas exchange with the outside air is limited.
But how do you get the CO2 in there?
You use a smuggler. In the outer cells of the leaf, the mesophyll cells, C4 plants use a different enzyme to do the initial carbon fixation, PP carboxylase.
And PP carboxylase doesn't make the same mistake.
It has a very high affinity for bicarbonate, which is just dissolved CO2, and it has absolutely zero affinity for oxygen. It ignores oxygen completely. It's a much better, much more specific enzyme.
So it fixes the carbon into what?
Into a 4-carbon compound, usually oxaloacetate or malate.
Yeah.
That's why it's called the C4 pathway.
So the smuggler, PP carboxylase, grabs the CO2, turns it into a 4-carbon package, and then that package is shipped into the VIP room, the bundle sheath.
Exactly. Once inside the bundle sheath cell, an enzyme decarboxylates the malate. It breaks it down, releasing a molecule of CO2. The CO2 concentration in that tiny room skyrockets, maybe 10 or 20 times higher than the air.
And it just floods Rubisco.
It completely overwhelms the oxygen. Rubisco, sitting there in the bundle sheath, is forced to work at its maximum efficiency as a carboxylase because it's just swimming in its preferred substrate. Photorespiration is almost completely eliminated.
It's a brilliant solution, a carbon concentrating mechanism. But if it's so much better, why aren't all plants C4? Why are my houseplants and the trees outside my windows still C3?
Because the smuggling operation costs money. It costs extra energy. It costs extra ATP to regenerate the PEP molecule that PP carboxylase uses. There is a trade-off.
So if you are in a hot, bright, dry environment where you have to keep your pores, your stomata closed to save water, which limits CO2 entry, then the C4 pump pays off handsomely.
It pays off big time. But in a cool, cloudy climate like Northern Europe, where you can keep your stomata wide open and get plenty of CO2 for free, the extra ATP cost of the C4 pump isn't worth it. C3 plants are actually more energy efficient in the shade or in cooler temperatures.
That is a classic biological trade-off. Adaptation is always contextual.
It is. There's no single perfect system, only the best system for a given environment.
We've covered a lot of ground today. I mean, we've gone from the quantum mechanics of tuning forks and excitant transfer to the manganese capacitor, the proton pumps, the complex shuffle of the Calvin cycle, and the elegant patch of C4.
It's a massive interconnected system.
When you step back and look at this entire picture, this whole story from Leninger, what is the synthesis for you? How does this fit into the Medlock Holmes saga of tracking energy?
For me, it closes the loop. It completes the circle. We started this whole series asking how life stays alive in a universe that tends towards disorder. We saw it fighting entropy. We saw it conserving energy in the form of ATP. Today, we saw the origin of that battle.
It's the first move on the chessboard.
Photosynthesis is the original act of conservation. The universe wants that photon's energy to just dissipate as heat in a picosecond. Photosynthesis says, no, I'm going to catch it, I'm going to separate a charge, I'm going to use that to build a gradient, and I'm going to hold that energy in a covalent bond in a sugar molecule for months or years.
Every beat of your heart, every thought in your brain right now is being powered by an electron that was originally excited by a photon probably millions of years ago in a chloroplast. We are just burning the sugar that they built. We are running the gradient back down that they pumped up.
It connects us directly to the sun. It's not just a poetic idea. It is a direct, traceable, metabolic fact.
And here's a final provocative thought to leave our listeners with. We talked a lot about Rubisco. It's slow, it's confused by oxygen, it's incredibly inefficient, and yet this flawed enzyme feeds the entire world. Leninger's textbook mentions in a box that scientists have been trying to engineer a better Rubisco for decades.
It's the holy grail of plant biotechnology. If you could improve it, you could dramatically increase crop yields.
But nature, with billions of years of evolution and unbelievable selective pressure, hasn't done it. Why? Is the inefficiency of Rubisco actually a mistake? Or is there some deep chemical constraint, some trade-off we don't understand yet, that makes the difficult chemistry of fixing a gas, like CO2, inherently slow and sloppy?
Perhaps its slowness is a feature, not a bug. Maybe it acts as a rate-limiting step that prevents the rest of the system from crashing when light levels fluctuate wildly. Or maybe the chemistry of carboxylation simply cannot be done with high fidelity without also having some affinity for the similar molecule, oxygen.
If we could improve Rubisco, we could revolutionize agriculture. But the nagging question remains, why hasn't evolution done it already? That is the question.
That is the multi-billion-dollar question.
Something to chew on. For our listeners, please go check the diagrams in Leninger. Look at the Z-scheme. Look at that manganese chair. It's really worth your time to visualize this incredible machinery. Until next time, keep diving deep.